Hello friends, welcome to another tutorial in electromagnetics and antennas series. In this tutorial we'll talk about vector magnetic potential, or sometimes referred to as magnetic vector potential. And I highly recommend that you watch my previous video on scalar magnetic potential in order to understand this properly. So if this is something that interests you, then please keep watching. A vector magnetic potential is referred to as A vector. That's the first key point. And it persists where current density is present. So that's the key difference between vector magnetic potential and scalar magnetic potential, and you'll understand it only if you see my previous video where we established that a scalar magnetic potential only exists when J is 0. However, vector magnetic potential will exist in the presence of J. And this new vector A that we just defined will give us B when we take curl of it. So curl of A will give us magnetic flux density B. So this is going to be our fundamental equation through which we'll derive the equation for A vector. We know from Ampere's law or from Maxwell's fourth equation that curl of H is J, and we know that B is mu naught H. So substituting the value of H, B upon mu naught, and taking mu naught on the right hand side, I get curl of B to be equivalent to mu naught into J. Then I take up this equation we started off with, and I take curl on both the sides. So curl of B on the left hand side will give me curl of A on the right hand side. And we have a corollary: del square A is equal to divergence of gradient of divergence of A minus curl of A. And I use this corollary here. So I get gradient of divergence of A minus del square A to be equivalent to mu naught J. And this thing is equivalent to 0 because gradient of divergence of a vector is 0. That's also discussed in the previous video. So I'm left with del square A is equal to mu naught into J, and that looks like Poisson's equation in magnetostatics. In electrostatics, we had del square V, which was electric potential, and that was equivalent to rho V upon epsilon. And we're going to use that anyway in our next slide. We refer to the Poisson's equation in electrostatics as del square V is equal to minus rho V upon epsilon naught. And I've done a separate video on Poisson's equation. You can refer that video in order to see the derivation of this to get a better understanding of this equation. Otherwise, voltage is referred to as Q upon 4 pi epsilon naught into R, and Q is charge. I can express charge in terms of charge density, which is rho V dV, volume integral. I substitute the value of Q here. So I get 1 upon 4 pi epsilon naught volume integral of rho V dV upon R. And if I compare this equation with the equation that I just derived, the Poisson's equation in magnetostatics, I'll find that my A vector turns out to be equivalent to mu naught upon 4 pi volume integral of J upon R. Alright. So J over here represents current density. Current densities can be represented in 3 different formats. So I can have 3 different expressions for A. I can have line current density, volume current density, and surface current density. And the line current density can be expressed as I dot dl, surface current density can be expressed as K dot ds, and volume current density can be expressed as J dot dV. This is one expression where we have taken into account the volume charge. So I get three different expressions for A, one for the volume, one for the surface, and one for the line. So that is how we can find three different expressions for A. Depending upon the problem or the numerical, we'll use any of these three. The volume integral will involve a triple integration, surface integral will involve double integration, and line integral will involve a single integration. Well, that's the basic difference between a magnetic vector potential from a scalar magnetic potential, that the magnetic vector potential A is dependent upon J, whereas the scalar magnetic potential Vm only persisted when J was 0. And that was it for today's tutorial. I hope you liked the content of the video. If you did, click the subscribe button and hit the like button as well. If you have any questions, you can ask me in the comment section. Share this video amongst your friends, that will be of great help. And take care of your health. I'll see you around in the next video to come. Take care. Bye bye.